Thank you guys for coming. We're recording this for Google Video. It's going to be available externally, so save your confidential or your proprietary questions till after they finish recording. Let's see. We're very fortunate to have with us Yakov, whose accomplishments in the field of networking are both distinguished and prolific. I personally would like to thank him for RFC 1918. Thank you. So without further delay, Dr. Yakov Rekhter. Thank you.
Is to talk about BGP. This year actually is kind of an anniversary of BGP because this year BGP is 18 years old. So if you look at the human being life when you're 18, it's kind of a big change for you. You graduate high school, you probably go to college, so you probably move away from your home. You kind of start to live on your own. So it's a big change for you. And in a sense, actually, BGP at 18 also kind of reached its own level of maturity. And what I want to do is to look at this 18 years of evolution of BGP and just share with you some of the lessons I personally learned from that experience, some of the lessons from the protocol design. And the expectation here is that what I hope to get is, by sharing these lessons with you, is that these lessons may apply to other things that you are involved in. So hopefully you'll be able to learn something from these lessons. So not to repeat some mistakes, and also to learn some positive things that I personally learned from that experience. If someone would ask me to condense all my experience to a single sentence, the experience I gained from working on BGP for the 18 years, that would be the sentence. In fact, that probably would be the overriding design principle that drove development of BGP for the last 18 years. That is, BGP from the beginning and until today had been always driven by pragmatism. The design of BGP, evolution of BGP, new features that had been introduced in BGP over these 18 years were mostly driven by fairly pragmatic, fairly practical considerations. So let's actually look in more details about the life of BGP over the last 18 years. And to understand it, we really have to step back and look at the dates that immediately preceded the creation of BGP. So we really have to step back and look at the environment in the late 80s. So what happened in 1987 is that National Science Foundation established a cooperative agreement with three partners: IBM, MCI, and Merit. And I happened to work at that time in IBM Research Center. That's how I got involved in this. So this cooperative agreement was responsible for building and operating what was known at that time as NSFNET Backbone Phase II. And the role of that network was to interconnect several research and educational networks in the United States. It was a fairly modest network by today's scale because it was fractional T1. And the number of sites that it interconnected was just 12 or 13. It was like under 20. Anyway, the interdomain routing protocol that was available at that time, the only one that was available at that time, was known as EGP2. It's Exterior Gateway Protocol 2. So let me just say a few words about this protocol because that will explain the driving forces behind the initial creation of BGP. Well, to begin with, this protocol wasn't exactly a routing protocol. That's why I put routing in quotes. It was just a reachability protocol. And therefore, it constrained topology at the level of autonomous system to a single spanning tree. And of course, at the root of the tree was BBN, who operated ARPANET. Well, the other problem with this protocol is that it was based on the notion that all the reachability information has to be periodically refreshed. That's how you know that reachability information is OK. And last but not least, it was running directly over IP. Well, so if you look at the creation of BGP, it was created in 1989 at 12th IETF, many, many years ago, many, many IETFs ago. And it is known actually as Three Napkins Protocol. And you'll see in the next slide why it's called this way. It was produced over lunch, so we didn't spend that much time actually designing the protocol. And it was produced pretty much by myself and Kirk Lockheed, who still works at Cisco. And we also got some help on this original design of a launch from Len Bozak, who at that time also worked at Cisco. Well, this slide actually explains why it's called 3 napkins protocol. We didn't preserve the original napkins because they were kind of stained with ketchup and a whole bunch of other crap, which we ate over lunch. But we converted these napkins into 3 pieces of paper, and that actually was the whole BGP. There was nothing else to it. So if you look actually at it, it's pretty much everything you need to know. This is the packet format. This is the description of all the codes and subcodes. This is the finite state machine. And here at the bottom, it's probably hard for you to see, but this is a contact information. It has email addresses and phone numbers, and even it has the working hours for each of us. Well, that was it. So people who right now produces 100 pages RFCs, I think they should look at this as an example of what really has to be produced. Well, as I said, it was produced in January of 1989. And a few months later, we had 2 interoperable implementations, one from myself and one from Cisco. And in June, we decided actually to finally document it as an RFC. That's how RFC 1105 was born. It was BGP, Border Gateway Protocol. Notice the sequence. First, very short specification. Second, interoperable implementations. Last is RFC. So what were the original design goals that drove the creation of BGP? Well, the goals were actually extremely modest, especially by today's standards. The original goals were just to overcome the limitations of BGP2. Specifically, at that point, we view as extremely unreasonable to constrain the inter-AS topology of the internet to a spanning tree with ARPANET being as a root. It just didn't fit, didn't match the reality. And that was probably the major problem with EGP2 that BGP was intended to solve. But there was other problem with EGP2 that we had to solve. And that is, as the volume of reachability information started to grow, we end up in a situation where this reachability information had to be carried over multiple IP fragments. Remember that EGP2 was running over IP. And so as you got into IP fragmentation, we ended up in a situation where some of the fragments could be lost. And as a result, we just had very severe routing flaps in the network because there was no reliable transmission of reachability information. In terms of scalability, the goals were fairly modest. It just to support a few thousand classful IPv4 routes. That was it. Nobody was aiming at 10,000, 100,000, million routes. It was like, who would even think about it? So just a few thousands. And the scope of it was also fairly limited. We just want to deploy it in the NSFNET backbone. From the beginning, it wasn't positioned as a long-term solution that is going to solve all problems for all people. Not at all. It was viewed as, some people call it hack. Some people call it short-term solution. I guess it's a polite name for a hack. And that's how it was positioned. Well, actually, if you look at the key ideas behind BGP, it's not that many. It's very few, and it's pretty simple, pretty obvious ideas. And they kind of were really nicely packaged together. That's what it's all about. So the first idea was that if you want to really have an inter-autonomous system routing protocol, not reachability protocol, but routing protocol, then you have to have some way to suppress routing information looping. Well, the way how BGP addressed this problem is by carrying the sequence of autonomous system numbers that routing information traverses. And that's how you suppress routing information looping. By suppressing routing information looping as a side effect, BGP also suppresses looping of the packets in the data plane. The second idea was also kind of pretty obvious. Instead of periodically refreshing the full set of routing information, you just send changes to the routing information. So you use technique of incremental updates. It's not a big deal. Well, because you use technique of incremental updates, BGP had to have some sort of reliable transport. And in this particular case, myself and Kirk Lockheed said, well, we're clearly not experts in the transport protocols. We don't have time to design new transport. We don't have desire to design new transport. And by the way, TCP IP stack already has a reliable transport. It's known in TCP as TCP, so what's the big deal? Let's just use it. It may not be perfect, but, well, it's probably good enough. Well, from the beginning, BGP had been known to attract a whole bunch of controversies. So the fact that controversy still exists with us today is nothing new. It's been there since day one. Well, let me just mention a couple of fairly controversial subjects that BGP attracted from the beginning. One thing which people argue against BGP is that BGP didn't support arbitrary routing policies. Well, the way how myself and Kirk addressed this problem is very simple. We said, look, it's absolutely true, guys, what you're saying. And that's OK, because what we have is a hack. We have a short-term solution. You guys want to work on a long-term solution that addresses all the problems? That's great. Go ahead, do it. We just have a short-term problem to solve. We'll just deploy it here. And later on, when we'll be ready with a long-term solution that solves all the problems for all the peoples, we'll do it too. The second controversy attached to BGP was that BGP decided to use TCP as a transport. Well, at that point, some of the people who claim to be, quote, internet architects start to argue against it because they said it violates certain architectural principles of the internet. Well, mind to tell you, they never able to point to us the specific principles where they documented. We've never seen them, but there was a claim it violates the principles. Well, the way how we addressed it is very simple. We said, look, we just have to be practical because we have a timeline to deploy the stuff. It was a real operational network. We can't be bogged down into this nebulous architectural principles. Again, long-term solutions wouldn't violate any architectural principles. Will be just perfect. It's just a short hack. So now let's just move forward and look at the evolution of BGP from its beginning, from its creation over the next couple of years. It's actually, as you'll see, we managed to go from version 1 to 2 to 3 at almost like either every year or every other year time frame. So what happened in BGP 2? Well, it was produced 1 year from BGP 1. What did we change? Well, the most important thing is that we changed the encoding. And the reason why we changed the encoding is because we realized that BGP, even if it's a short-term solution and even it's hack, it'll probably going to stay with us for a fairly long time. And therefore, we have to make BGP fairly extensible. As a result, what we did is we decided to carry all the routing information as a collection of attributes. Moreover, we realized that as protocol evolves, as its functionality evolves, some of the attributes may be necessary in all the cases. Some of the attributes may not be necessary in all the cases. So we classified attributes as mandatory and as optional. And of course, to make it extensible, we encoded attributes as a variable length field, type length value, which was also kind of a fairly new concept at that point in the TCP IP protocol stack, which was very heavy, kind of oriented towards fixed length field. Well, we eliminated one of the features which discovered to be useless, which was present in BGP 1. So we see right now, 1 year from experience, we just pruned feature which is useless. Well, we added new feature, authentication. Well, mind to tell you, later on we discovered that this feature turned out to be useless too. Well, we got rid of it as well, later. Well, 1 more year, and we have yet another version of BGP, BGP 3. Well, there was a little bit of optimization with respect to exchange of information about previously reachable routes. And then we also added another mechanism that would restrict a pair of BGP speakers to the single BGP session. Well, it's probably this mechanism in retrospect wasn't such a great idea. It probably was a mistake, in fact, in retrospect. So what we're doing right now, there is a work in progress to allow multiple BGP sessions between a pair of BGP speakers. 1 more year, 1992, BGP 4. That is really a very major milestone in the life of BGP. And the reason why I'm saying this is because it's BGP 4 that moved internet addressing architecture from the notion of classful addresses to classless interdomain routing known as CIDR. I don't know, you guys are fairly young here, but those of you who have been around this area for long enough time may remember days where there was Class A networks, Class B networks, and Class C networks. Well, nobody knows about such things today, but they did exist at that point. And what CIDR did, it said, look, it's really stupid to have different classes of networks. These are all address prefixes and different blocks of addresses. That's all what it's about. And it really had a profound impact on the internet because it's precisely CIDR and BGP4 that enable the internet scale to what we know as internet today. Well, in terms of the protocol itself, it actually didn't require that many changes. The only thing we changed is how we encode reachability information. In BGP 1, 2, and 3, reachability information was encoded as a collection of Class A networks, Class B networks, and Class C networks. Well, since in CIDR you don't have it, you encode reachability information just as variable length prefixes. Notice again, it was widely deployed in the internet around 93, and about a couple of years later, after it was widely deployed, it got even published as an RFC. Again, notice the pattern. First specification, then deployment, then RFC, which is very different from the sequence of events we witness today in the internet. Now let's move forward and look at the life of BGP in mid-90s. And clearly, I'm not going to cover all of the things that happened in BGP in mid-90s. I just want to focus on two particular developments. One is replacement for I-BGP mesh, and second, route filtering. Well, to understand the I-BGP mesh replacement, we again have to go back to the original design of BGP. BGP, prior to I-BGP mesh replacement, had to distribute routing information both within its own autonomous system and across autonomous system borders. And so within its own autonomous system, the way how BGP 1, 2, and 3 was designed was very simple. Essentially, you have to establish BGP sessions with all of the border routers within its own autonomous system. And it was done for a very simple reason. It was pragmatic. It was expedient. It was really simple to implement. And I can attest to it because I implemented it myself. Well, and this mesh actually wasn't really a big practical problem from the beginning because the internet was small, because all of the ASs were fairly small. We recognized this could be a potential problem from the beginning. We knew it from day one. However, we decided kind of to put this problem on the shelf to see when it will become a real problem. Well, it became a real problem in mid-90s for a very simple reason. Because you had more widespread deployment of BGP, and because the growth of the internet, so each autonomous system started to get bigger and bigger. So this I-BGP meshes started to get bigger and bigger as well. Well, mid-90s produced not one, but two replacements for I-BGP meshes. One was known as BGP configurations, and second as BGP route reflectors. The BGP configurations is a very simple approach. It follows the divide and conquer strategy, where you take your autonomous system and you chop it into several sub-autonomous systems, sub-ASs. And then you have meshes within only its sub-AS, but not across sub-AS boundaries. Pretty straightforward. BGP route reflection is a different approach because, in effect, it replaces this notion of full mesh I-BGP with hub-and-spoke topology. You may ask me a question whether both of these were needed at that time. I really don't know. It's a water under the bridge. It just happened that both of them were developed at about the same time. Keep in mind, both of them actually solve exactly the same problem. You may also ask me, do we still need both of them today? Well, for that I can tell you the answer is yes, for a very simple reason. Because both of them are deployed today. And for an ISP who uses route reflection, there is very little, if no incentive, to transition to BGP confeds. And vice versa, for an ISP who deploys BGP confeds today, there is little or no incentive to transition to route reflection. So it's kind of, for whatever reason, just because they were created both at about the same time, we just now have to live with both, and probably will live with both for a very long time as well. Now let me talk about second area of development of BGP that happened in mid-90s. That is improved route filtering, which is also actually very important from a conceptual, from functionality point of view. Yet from implementation point of view, it was pretty simple. Now, you have to keep in mind that the ability to constrain distribution of routing information is one of the key requirements for any inter-domain, any inter-autonomous system routing protocol, which means it's also a key requirement for BGP. Well, the way how it was originally done is filtering was done based on the address prefixes. And it was really complicated and very kind of labor-intensive in terms of configuration. So mid-90s introduced the concept of BGP community. Well, what BGP community does, effectively, it allows us to mark a collection of arbitrary routes with a single marker, and then use this marker for the purpose of route filtering. What was interesting about this mechanism is that, first of all, it's a fairly general mechanism because, as I said, you can mark arbitrary set of routes with a common marker. And once you mark them, you could filter based on that marker. What is also interesting about this mechanism is that community space from the beginning was partitioned into two parts. One that has global semantics, which is known as well-known communities, and one that has local semantics, which each autonomous system could assign on its own and attach its own semantics to it. And actually, it turned out to be very useful because it gives some ability to have globally consistent behavior on certain communities, for well-known communities. But it also allows each ISP on its own to create its own policies without going and getting agreement from the rest of the universe. Well, let's move forward and let's look at the evolution of BGP in late 90s. And again, I'm not going to cover all of the things that happened in BGP during this time frame. I'm just going to talk about three particular areas: authentication, multi-protocol, and capability advertisements. So let's start with authentication. Well, when I talked about early days of BGP, I mentioned that BGP 2 introduced this notion of authentication by using the marker field. If you ask me why did we do it, I can give you a very honest answer, because ISG and IAB at that time said that you have to have authentication. And we asked them, what do we need to do authentication? I said, well, put this 16 bytes marker field. They said, sure, no problem. Well, of course, reality showed that this is totally useless. Well, to begin with, actually, it was useless for two things. First of all, it was underspecified. Well, if it's underspecified, it clearly cannot be implemented by multiple vendors. So it wasn't implemented to begin with. But even, let's say, for the sake of argument, we would fully specify it. And let's say, for the sake of argument, that vendors would implement that. It really had a fairly fundamental problem, this idea. Because what you've been trying to do with this, you've been trying to authenticate BGP. And that's really great, except that you missed a bigger hole which sits underneath of BGP, which is TCP. So you can authenticate BGP as much as you like, but if somebody would attack TCP underneath, your BGP authentication does nothing. Well, so what we realized at that point is that we really should be authenticating not BGP, but TCP. That's what should be authenticated. And so what late 90s produced is known today as TCP MD5 authentication. It's a pretty straightforward thing. You just authenticate TCP connections. Well, as a side effect, because you authenticate TCP connections and because BGP runs directly over TCP, you authenticate BGP connections as well. So it's pretty straightforward, kind of pretty obvious, in fact. It's been implemented by many vendors for many years. Yet, if you look at today's deployment, it's still fairly limited. And of course, you can ask the question, why? I'll talk about it later when I'll talk about securing BGP. Let me talk about second major development that happened in BGP in late 90s, and that's the multi-protocol extensions. Again, to understand motivations for that particular development, we have to step back in time and look at the situation prior to late 90s. Well, remember that from the beginning, BGP was designed as IP version 4 routing protocol. And that was all fine, except that in mid-late 90s, Internet introduced yet another version of IP, known as IP version 6. Well, if you're really serious IP version 6, you really have to have not just intra-domain, but also inter-domain routing protocol for IP version 6. So at that point, IETF people and ISPs asked, how are you going to have inter-domain routing for IP version 6? It was a valid question. Another valid question that was asked at that point is that if you have unicast and multicast at the interdomain level, and you don't want the two to be completely congruent, then how would you actually accomplish this at the interdomain level? Well, at that point, we had two options on the table. The first option was to take what is called as interdomain routing protocol, I-BGP, which was developed in ISO. And from a functional point of view, it was multi-protocol on day one, and it actually was a functional superset of BGP4. So that was one option. The second option was just to take BGP4 and extend it. So let's see how these two options had been played out. Well, the choice was to go with the second option for a variety of reasons, and all of them were good, in fact. Well, so let's look at some of the reasons why the choice was made to extend BGP rather than to implement and deploy I-BGP. Well, we knew it was pretty much obvious to us that from the functionality point of view, BGP didn't have and still doesn't have as many features as I-BGP. And we knew it for a very simple reason, because I've been very much involved in the development and design of I-BGP as well. So I knew it by myself. But at the same time, we also knew that from an implementation point of view, the additional incremental efforts of extending BGP would be much less than what it would take to implement I-BGP from scratch. Also, even if I-BGP formed a huge functional superset of BGP, it wasn't clear at that time, and in retrospect, actually, it's still not clear even now, whether all of the features that had been present in I-BGP would ever be needed in practice. Remember, I-BGP was designed in OSI standards, and in OSI, people really like to think big, like to think about long term, like to predict the future, and of course, they all have crystal balls. So again, it was a fairly pragmatic way of addressing the problem. You solve what had to be solved, and that's it. But what we did is we said, well, we really have to solve the problems I mentioned on the previous slides, but let us not just focus on a point solution. Let's just solve them in a fairly general fashion, and that's exactly what we did. Well, the way how we address this is by introducing multi-protocol extensions, where you should be able to carry addressing information associated with a variety of network layer protocols. And initial focus was on IP version 4, IP version 6, and probably OSI. That was the initial focus. The implication actually of doing this, we didn't anticipate all the implications of doing this. And probably we still don't understand all the implications of doing this. But the implications are enormous, and I'll talk about it later on. The most important part actually of doing this is it enables BGP to be used as a protocol for extremely wide variety of applications. And I'll talk about some of the applications of BGP that BGP is used today for. Now let me talk about yet another development that happened in the late 90s in BGP, and that is capability advertisements. And again, to understand the motivations for this particular development, we have to step back and look at prior history. Well, the question you may ask is that as you introduce new features in BGP, how would a router find out what its neighbor is capable of? Well, in traditional protocol design, there is a well-known textbook approach to deal with this. It's called the version number. And in fact, this textbook approach had been used by BGP from the beginning until we hit BGP version 4. We had version 1, 2, 3, and 4. And it's kind of okay, except that we realized that if you have a whole bunch of independent features, then this approach isn't going to work at all, for a very simple reason. Because if you have n independent features and you want to advertise a particular subset of these features that you support, then it would require probably 2 to the power of n different version numbers. So the version number field, to begin with, probably is going to be very large, and it probably wouldn't make any sense to figure out actually what are you doing. So that actually led to the development of what is known as capability advertisements. The idea, again, is very simple. So instead of mapping a particular set of features to a given number and call it protocol version number, we just advertise support for individual features. In a capability advertisement, we advertise it at the session establishment time. What it does, it provides us a much more flexible and, in fact, much more explicit and direct way of introducing new features. So the first new feature that actually used this capability extension was the BGP multi-protocol extensions. But there had been a whole bunch of other features that use this capability. And it's precisely because of this feature, precisely of BGP capability advertisements, that today, more than 10 years since BGP4, in fact, almost 13 years from BGP4, we still have exactly the same version, despite the fact that BGP, as we know of today, has a whole bunch more stuff than the original BGP4. So let's move forward and look at late 90s, beginnings of the 21st century, and let's look at new applications of BGP. As I mentioned, the introduction of multi-protocol capabilities, one side effect of it was that BGP started to be used by applications that pretty much have nothing to do with the internet. The first one was BGP MPLS VPNs, known usually as 2547 VPNs. It was introduced in 1998. That was followed by auto-discovery for VPNs in 2000, and followed by BGP-based virtual private LAN services, VPLS, 2 years later. All this had been made possible by one thing, actually by two things. It's a combination of multi-protocol extensions and capability advertisements. And of course, actually, we shouldn't underestimate all the previous work that had been put into BGP, because all of these applications reused all the previous extensions of BGP, as is, pretty much. What is interesting about this development is that these developments extended reachability information carried by BGP well beyond traditional IP reachability information, well beyond IPv4 or IPv6 address prefixes. And this stuff generated so much controversy, you wouldn't believe it. People really got very emotional. If you would look at some of the emails that had been floating around, and still kind of floats around about the stuff, it's just incredible how emotional people got about it. So let's look at some of the controversy. Well, some of the arguments against doing all of this was based on the claim that BGP shouldn't be used by such applications as 2547 VPNs, VPLS, etc. Why? Well, the claim was because BGP wasn't designed to support these applications. I would be first to admit it's a true statement. It's absolutely true that BGP was not designed to support these applications. In fact, when BGP was designed, we didn't even know what these applications are. Well, but if you look at this argument, then I could also make an argument saying that in the beginning, BGP wasn't designed to support CIDR. It wasn't designed to support 200+ routes in the internet it supports today. It was designed to support just a few thousand of classful routes. It wasn't designed to support IPv6. And this list could continue on and on and on. So clearly, look, guys, this is totally bogus argument. What really matters is not what BGP was designed for. What really matters is what BGP can do in a cost-effective manner. That's what really matters. Well, the second argument in this controversy was that BGP shouldn't be used by applications that require to carry, quote, non-routing information. Again, why? Well, because BGP was designed to carry only routing information. Well, so based on this argument, people say, well, you can use BGP for IPv6. That's OK, because it's routing information. But you certainly shouldn't use BGP for such thing as virtual private LAN service, because in this case, BGP carries non-routing information. Well, to begin with, in this kind of argument, the first question you should ask is, what is exactly, quote, routing information? Which I was never able to get a straight answer to that question. But again, look, it's totally a bogus argument. Again, it's a dogma. Why do you care whether the information is routed or not? What really matters from a practical point of view is whether it's a good or a bad fit between the requirements for the distributing information and what BGP can do. And if requirements for the distribution of information could be reasonably met by BGP, let's go ahead and do it. And if it couldn't be met by BGP, it really doesn't matter whether it's routing or non-routing information. BGP is not a good tool for that. Well, another argument that was made against using BGP for all these non-internet related applications is they said, well, it gets more and more complex to implement BGP. It's a true statement. I would be the first to admit it again. However, let's just face a few very simple facts. If there is a market demand for a particular functionality, then believe me, router vendors are going to supply it because we live in a market-driven economy. There is no magic for that. So this functionality will be implemented no matter what. The only choice on the table is that whether you're going to implement this functionality by extending BGP or by inventing a brand new protocol. Well, and if you look at it from a system-wide perspective, actually, extending BGP makes much more sense than inventing new protocols because from the overall point of view, system gets less complex. Again, keep in mind, as long as this new functionality matches reasonably well what is already provided by BGP. And look, yes, you do make system more complex, but overall, if you look at these two options, one, extending BGP, and second, inventing new protocols, you will realize that the overall system complexity is going to be less with the first option than with the second. Well, another argument that had been made against extending BGP in support of new applications is they said, well, you're adversely impacting the overall router software reliability. Why? Well, because you're creating software bugs and extensions, and if I'm an ISP and all I care about is IPv4 routing, and you write this extension to support 2547 VPNs, and you have a bug there, well, you may crash my internet service. Well, it's kind of also a dubious argument because, first of all, if you want to add new functionality to a router, you may introduce bugs no matter what, and they could crash your bugs. So what you really have to look is how much more you have to add to a router, how much more software you have to a router. Well, you have to remember, it's a basic software engineering. Then more protocols means more lines of code. And what is very important is that the number of bugs you're going to introduce tends to be proportional to the number of lines of code you have to add to the system. So actually, by extending BGP, you're going to actually reduce the number of bugs relative to the other option, the option of inventing and implementing a brand new set of protocols. And the last but not least, look, there is no magic. And we have to remember that in the end, what really matters is a competent system design and a competent software engineering. That's what really matters. And if you have good system design and good software engineering, then in fact you could avoid problems I mentioned here in this slide. So now let me move to another topic, which is also somewhat controversial, and that has to do with securing BGP. And we all like to talk about security in various dimensions applied to various subjects, and clearly BGP is by no means an exception. So people like to talk about securing BGP. When we talk about securing BGP, I think the first question we have to answer is, what exactly are we trying to secure? What problems are we trying to solve? And this answer has actually multiple questions. At the most basic level, all you have to do is to authenticate the peer. Well, as I said, that had been implemented a while ago, known as TCP MD5 authentication. And as I also mentioned, it still has a very limited deployment. There are two other proposals on the table that had been floating for a fairly long period of time. One is known as Secure Origin BGP, SOBGP. No deployment, despite the fact that it's been around for probably 4 or 5 years or even more. And the second is even a superset of the second. The third one is a superset of the second one, is that you authenticate not just the originator, but the whole AS path that had been traversed by the routing information. That is known as Secure BGP, SBGP. Again, had been around for quite some time, and again, just like the previous one, no deployment whatsoever. And you should ask yourself why. And I think there is a very simple reason for this. You have to look at the cost, and you have to look at the benefits. You have to look at who is going to bear the cost. You have to look at who is going to reap the benefits. Look, if cost-benefit analysis doesn't justify deployment, it doesn't matter how great it is. It wouldn't get deployed. If those who bear the cost are not those who reap the benefits, it will never get deployed. You also have to ask, can it be deployed in incremental fashion? Because if you require the whole internet to deploy a particular technology before anyone could start to reap any benefits, you're clearly setting yourself up to absolutely unreasonable goal. Also, even if it could be deployed in incremental fashion, you really have to be able to start reaping at least some of the benefits in a partial deployment. You cannot sit and wait till everybody deploys it until you start to get benefits. And last but not least, we really have to keep in mind that Internet today is composed of business ISPs. And these business ISPs do compete with each other. And therefore, their interests of individual ISPs may not always be well aligned with each other. So now let me just say a few words about some of the fairly recent enhancements of BGP. And again, I'm not going to go through all of the areas of recent BGP development. I'm just going to focus actually on just two, on just one actually, route target constraints. Well, to understand this particular enhancement, route target constraints, we have to remember that one of the main goals of BGP is actually to distribute routing information, but also to constrain distribution of routing information. And I talked about how communities had been used to tag routing information and then use route filtering to constrain distribution of routing information. Prior to route target constraints, actually, these route filters themselves were constructed via configurations on the routers. So if you want to filter a particular set of routes, you tag these routes via configuration with a particular community, and then in the configuration, you specify that all the routes that have a particular community should be filtered out. Well, what route target constraint introduces is that it uses BGP for the purpose of distributing these filters themselves. So in a sense, actually, you may think about route target constraints as a recursive use of BGP. It's actually, you may think about it as a pretty straightforward idea. But from a conceptual point of view, again, it's a very major milestone in the development of BGP because it creates recursive use of the same protocol. And I don't think you'll find any analogy to this in any other of the routing protocols used today in the Internet. So in the conclusion, I guess over this 18 years, one of the important lessons we learned is that the evolution by trial and error is just fine. You shouldn't be afraid to introduce new features. Don't get excited about it. It's all fine. And you shouldn't debate whether a new feature is useful or not. You'll never find it out. You should test, use operational experience to determine whether a feature is useful or not. Because, look, you can debate until you turn blue in the face. It's not going to get you anywhere. And if the operational experience tells you that the feature is useless, that's OK. Cut the losses. Get rid of it. So what is important, if you have this in mind, is that you have to design protocol from day one that could easily facilitate addition or deletion of features. That's what you really have to focus on, not on debating whether a feature is useful or not. Well, another important lesson we learned about BGP is the notion of in-time development. We're not going to sit and anticipate all problems that are going to happen 10, 20, X number of years from now. We focus on the short-term problems that we either face today or going to face like 2, 3 years from now. And solving this problem in real time with emphasis on solid engineering. So as a result of it, you don't spend too much time on solving, quote, anticipated future potential problems because, look, the list of these problems is unbounded. So as a result, you can spend unbounded amount of time just worrying about these problems. And if you have this model of operations, what you really have to focus on, you really have to maximize reuse of the existing mechanisms if you really want to have just-in-time development. And the way to do it is to make new mechanisms sufficiently general. That's step number one. And to pretty much be satisfied with good enough match between what is required and the existing mechanisms. Don't aim at the perfect match. Perfect match doesn't exist. Be happy with good enough match. Well, finally, let me just say that one thing we learned from BGP, and actually I learned it from other technologies I've been working on as well, is that short-term solutions tend to stay for a very long time, and long-term solutions tend to never happen. It's just a fact of life, and we just have to live with this. Another important lesson I learned from BGP is that good enough solutions are just fine. You don't have to look for a perfect match. Perfect solutions are not necessary. And again, you're going to waste a lot of time perfecting your solution, and you probably miss the market. I personally don't believe in crystal ball. I don't have crystal ball. When people ask me to predict the future, my answer to them is that I'm not a prophet. And with this in mind, I think will be much better off to addressing the needs of a market by focusing on technology that is flexible and extendable, rather than by trying to stare at this crystal ball and predict the future. And last but not least, development of BGP certainly teaches us that we shouldn't be afraid at all to question and violate, if necessary, any dogmas, even if these dogmas are wrapped into this, quote, architectural principles. And let me just repeat what I said at the beginning. There was one, and there is still one, overriding design principle behind BGP, and that is pragmatism. It stayed with us for 18 years. It served us really well, and I just hope it will stay with us again. And that's the end of my talk. Any questions?
Multiple decision sequences into BGP. Right now we have fairly flexible decision sequences.
Okay, I'm going to repeat this question because I've been asked to repeat it for the benefits who are on the video. So the question was whether we are going to introduce multiple decision sequences in BGP, because I guess the claim is that BGP right now is fairly inflexible in terms of decision sequences. Let me ask you, before I answer your question, I have to ask you a question. What exactly do you mean by multiple decision sequences?
For the same set of routes, we normally go by local pref, then by ISPF, then by IGP metric, and finally by router ID.
Right, so the answer to my question was that BGP has right now kind of a fairly well-defined route selection process. And the question is whether we could modify this route selection process. Well, the route selection process is fairly fixed, but you have to keep in mind that as part of this route selection process, you have a field known as local preference. And the router could set local preference to whatever number it likes. So it's a purely local decision. And that gives you all the flexibility you need in terms of altering outcome of the route selection process. So the machinery is there. Whether you use it or not, well, it's your local choice. Any other questions?
I'm going to ask mine into the mic to save you the trouble of repeating it. So back in...
No, close to the mic.
Back in 1990, probably late 95 or so, when confederations were starting to get deployed, we had a global event where someone leaked confederation details into the global internet. And all of us who ran GateD at the time wound up having our BGP sessions flat because GateD's implementation didn't understand the AS set and AS sequence elements of the AS path attribute. I'm curious how that event fed back into the protocol design process, if at all.
Well, actually, BGP deployment during its lifetime witnessed several kind of big meltdowns. So that was one of them. I remember quite well another meltdown when it wasn't the fault of BGP, but it was still a meltdown. When people redistributed BGP routes into IGP, it happened in several ISPs, and it just melted down completely. Look, the example with, actually the first and the second example are the cases of misconfiguration. The leaking was because of misconfig, and so its redistribution was due to misconfig. BGP can build only that much protection. I guess it's a cost-benefit analysis, and look, you can protect against your own mistakes only that far. You're not going to get bulletproof protocol. I'm sure today you can probably melt down something in the protocol as well if you don't do it. What BGP does have is this notion of well-known versus optional attributes. And so if, for example, confed stuff would be encoded with optional attributes, it probably wouldn't cause GateD meltdown, but again, it's water under the bridge at this point. Yes?
So TCP MD5 authentication seems to meet the criteria that you laid out in that it provides incremental benefits. Why is it not? Why do you feel it's not widely deployed today?
The question was that TCP MD5 gives you incremental benefits, and why is it not widely deployed today? You know, I have exactly the same question as you do. And I don't have a good answer to your question. I guess my answer to this is cost-benefit. ISPs look at cost, look at the benefits, say, well, not worth it probably. Remember, all it does, it protects you against certain attacks at TCP level. Probably there is not enough of these attacks to justify the cost of deploying it. If there'll be more attacks, probably ISPs would pay more attention to this technology, because from a deployment point of view, it's not that hard. There's another thing related to this, is that the original TCP MD5 design didn't have any mechanism to facilitate changing keys. Okay, so if you want to change keys, you pretty much have to coordinate with your neighboring ISPs, change the key. There is a work going on right now done by both Cisco and Juniper that allows to support the keychain. That clearly facilitates a lot this issue of changing keys. Whether that would make a big difference, well, if you have a crystal ball, I'm sure you'll tell me. I don't. Yes?
What about the impact of having the TTL hack as an alternative solution to authenticating next hop?
The question is, what's the impact of TTL as the quote hack to do authentication? Well, it does authentication only at the inter-AS boundaries. It still doesn't help you for the I-BGP sessions. Look, again, you can do it, but again, look at the cost, look at the benefits. Yes?
You have mentioned something about the recursive protocol usage.
Yes.
And I'm going to know your opinion about a situation where you use BGP to provide next hop information for reachability provided also by BGP.
The question was about recursive protocol usage, and the question was about using BGP to provide reachability information to resolve the next hop, which is carried by some other BGP. Well, in fact, actually, that's been done for relatively long time. That's how 2547 works. And it's been deployed, and it works just fine. So it's a perfectly fine idea. The notion of, actually, one thing which BGP introduced is the notion of recursive next hop resolution, because the next hop you carry in BGP, especially in I-BGP, is not something which you can reach directly. It's address of some other ASBRs in your network, and you have to resolve that next hop into your immediate next hop. And you could recurse it one more time and say, well, the next hop which you carry in I-BGP is actually may not be directly reachable even via IGP, so I have to look into my BGP to resolve my next hop. It's a perfectly fine thing to do. And as I said, it's been deployed.
So it seems to me that the fundamental limitation, although BGP has been extended many times, is the fact that every router chooses its best route and is only allowed to announce that best route. So effectively, information gets lost. I realize this is one of the reasons why BGP scales so well in today's internet, but effectively you're throwing information away that if we kept that information, it would enable us perhaps to make better routing decisions. So do you think BGP can be extended in a sense, or do you think that the limitation is so fundamental that we would require another protocol to do this?
Do I have to repeat the question? Well, let me start answering this question from the back. And that is, BGP certainly could be extended to carry additional routes. And in fact, there had been several proposals, had been floating around for a fairly long time, probably like 5 or 6 years, to carry additional routes, multiple routes in BGP. But as you said yourself, there is no such thing as free lunch, and as a price of carrying additional routes, you also have more resource consumption. And I guess ISPs look at it, and the trade-off was not in favor of carrying more routes. Trade-off was in favor of carrying less routes, even if it limits your choices. So in principle, it's possible. It could be done. In practice, it's again cost-benefit.
Okay.
Yes?
Go.
Would we ever be able to prefer routes based on bandwidth?
Sure, assign local preference based on bandwidth.
No, that doesn't work, actually.
Pardon me?
That's in the situation that we're working with, that's not there.
See, the question was whether it's possible to prefer routes based on bandwidth. Let me tell you something, that there is an existing implementation that actually prefers routes based on bandwidth. It's a 2547 case, and the case actually is very simple. When you have a site which is multi-home to a service provider, and it has different capacity links. One, let's say, T3, another is backup multiple T1s, bundles of T1. So there is BGP extended community that's called link bandwidth. And in this case, routing decision takes into account, among other things, link bandwidth. So I have an existence proof that, yes, it is possible because it's been implemented and deployed.
We have time for one more question. They have a question in Dublin.
Go.
Sorry. There are some intention by Internet regional registries to start assigning 4-bit ISNs. And original BGP specification is limited to 2-bit ISNs. In fact, some of regional Internet registries already assigning 4-bit ISNs, while protocol is still not extended. And what do you think about this situation?
Well, actually, the statement that protocol has still not been extended to support 4 bytes ASNs is not correct. I know that Internet Draft, and I think it's already published as RFCs, that supports 4 bytes AS numbers. And in fact, I know that it's been implemented by Redback for quite some time. I know that Juniper doesn't have it yet. I don't know whether Cisco implements it. But protocol had been extended to support 4 bytes AS numbers. OK? Thank you. One more question?
If you have more questions.
Sure. More questions? OK, guys. Thank you very much for inviting me here.